Unmute. I feel like I should just wear a shirt that says you're on mute. Welcome everybody. Thanks for joining us for our virtual open house session this afternoon. So my name is Cassie. I see a lot of familiar usernames here. So thank you for those who are returning as people are starting to come back in. I see a few new names, so I'll introduce open house, Lamont, our speaker, a little bit, and then we'll get things started. So as you know, you're all tuning into Lamont's virtual open house. Lamont is an earth science research organization, and we're located in Palisades, New York, and we're part of the Earth Institute at Columbia University. The Earth Institute is actually made up of many different centers, and Lamont is the largest piece of that. And we have been around since 1949. Our first director, Doc Ewing, was the one who decided to start open house as a way of opening up our science, our facilities to the community. And we've probably continued to do open house since then. And this is our first virtual event. And we're really excited to be offering you a great lineup of speakers, both for K-12 audiences as well as adults. And you can find all the information on our website. And today we're very lucky to have Nicols Young, who's a Lamont Associate Research Professor in our Geochemistry Department. If you signed up for our LDEO to go packet, he is the superhero scientist that is featured on the postcard, and he'll tell you all about his superpowers during his presentation. We're going to be utilizing the Q&A box today. So if you do have questions, feel free to type them in throughout the presentation, and we'll be sure to get to those after. So Nicolas, without further ado, take it away.
Okay, thanks everyone for showing up. Let me just get this good to go. And I think this should look good. So thanks everyone for joining. My name's Nicols Young, and I'm a geologist and a geochemist at Lamont Doherty Earth Observatory. And I'm going to show you a bit today sort of what it's like doing field work on Greenland. And so this is the main area that I work. And this original slide that you're showing right here, that I'm showing right here, is this is a picture of Greenland. So this is on southwestern Greenland, and it's at this glacier called Jakobshavn Isbrae. And that's sort of this thing you can see here in the background. And this glacier is often considered the fastest flowing glacier on Earth. Sometimes it reaches speeds on up to 12 miles a year. So in glacier terms, that's really fast. And this is a camp that we set up in 2018. And so this landscape you see here with all the boulders around and all the bedrock, probably as little as 10 years ago, it was actually covered by the Greenland Ice Sheet. So in the last 10 years, the ice sheet has removed itself off this landscape, and this sort of like moon or Mars type landscape that you see now is what's left. And these little tents here are where we might sleep. And this big dome tent right here is where it's sort of like our living room. It's where we cook our meals and sort of hang out in the morning or in the evening when we're not working. So, okay, where's Greenland? Greenland is that big white thing there right in the middle. And just to orient yourself, the star down here is New York City. And then Hudson Bay, Alaska's over here, Atlantic Ocean, this would be Iceland, Europe's over here. And so again, I do most of my work on Greenland. And it's the only ice sheet we have in the Northern Hemisphere. So it looked like yesterday there was a talk on Antarctica. If you tune into that, that'd be in the Southern Hemisphere. And so there used to be a second ice sheet, which covered almost all of Canada and actually extended down to New York City. So if you live on Long Island, the only reason Long Island is there is because the last time this ice sheet existed, which we call the Laurentide ice sheet, it left or deposited what is now Long Island. And so about 20,000 years ago, that ice sheet started to disappear. And so it retreated all the way across Canada. And all that's left is this little sort of bowling pin thing right there that I'm circling, which is called the Barnes Ice Cap. But I guess for today, I'll just speak a bit on what we do on Greenland and what it's like doing field work up north. Okay, so here's what Greenland looks like today. This large island is almost entirely covered by the ice sheet. So the ice is obviously in white. And then where there's no ice sheet, you have this little bits of land that are exposed, which sort of appear in shades of brown and green. But 20,000 years ago, the ice sheet was actually much bigger. We think it probably looks something like this. So it extended out into what is today the ocean. And so between 20,000 years ago and today, this big ice sheet shrunk towards what we see today. But we're also interested in what the ice sheet might look like in the future. So here's just sort of a cartoon on what Greenland might look like if you removed all of the ice off Greenland. And we actually know this has probably happened in the geologic past. And we know this because way up at this point here, that's called Cap Copenhagen, some really smart Danish people, they dug around in the dirt up there, and they found the remnants of white cedar. So this is a tree that exists today in much of New England and in like southern Canada. But we found it way up in northern Greenland. And so there's no trees on Greenland today. So basically the only way you can probably get a tree all the way up on northern Greenland is if there was no ice sheet at all. And you'd probably have to have temperatures be like 8 degrees warmer than they are today to completely get rid of the ice sheet and have these white cedar trees growing way north on Greenland. So one thing we're really interested in is how does the ice sheet go from something big like this to something a little smaller like we see today? And so I'm going to focus in on this region. This is in southwestern Greenland. So here's this box, and then here's the blow up of this box. And so you can see the ice sheet, it's here in white. And then this is all just ice-free land right now. And this is where we primarily do our work. So we're pretty interested on when in time did this area become ice-free? So when was the last time this area had ice over it? And so how do we get to Greenland? Well, usually the US Air Force flies us over in these big cargo planes. It can be pretty fun. It's a bit cold up there since it's not sort of they're not made for commercial passengers and it's not the most user-friendly experience. But they do fly us over for free, so that's great. So this is us getting on a US Air Force plane actually up near Albany, New York. And then when we get to Greenland, we get on a helicopter to take us way out into the remote backcountry to where we want to work. So here's a typical helicopter we might use. And then this is the helicopter after it had just dropped us off in the field. And you can see here's all of our gear here. So this is some of our scientific equipment. So here's probably some of our tents. There's a battery right there. Here's the pilot. Most of the pilots on Greenland tend to be ex-Danish military pilots. They're actually really great. And then what we want to know is when did this area, so say like back in this picture, like these hills and stuff, when did they last become ice-free? Or when was the last time they were covered by ice? And so here's maybe the true like real science slide you're gonna see over the next few minutes. And we use this technique called Beryllium 10 exposure dating. So how does this work? What you're looking at here is a picture of the Greenland ice sheet in the background. And then here's one of our friends sitting on a rock, sort of contemplating life, looking out at that ice sheet. And the Earth is always being bombarded by cosmic rays. And so where do these cosmic rays come from? So you may have heard of the term a supernova. So when stars explode in outer space, they shoot all of these rays all over the universe. And they actually enter the Earth's sky or the Earth's atmosphere. So they enter the Earth's sky, and then when they get into our atmosphere, they start running into other particles that are hanging around in the sky. And so the incoming cosmic rays, they crash around with all these particles, and it sort of begins a chain reaction that happens all the way through the sky until it reaches the Earth's surface. So now you have these really fast moving particles that slam into the Earth's surface. And so one thing that they do is they slam into rock that is exposed to the atmosphere. And one of the byproducts of this collision is this isotope or element that we call beryllium-10. So you can imagine in this picture, the ice sheet back here at one point in time was actually covering this rock where our friend here was sitting on. But when the ice sheet melted and retreated off that rock, these particles were allowed to hit it, and so beryllium-10 starts forming in this rock. And the best way you can think about it is it's kind of like the rock is getting a suntan. So the longer that rock sits out exposed to the sky, the more beryllium-10, or like the more intense suntan it will have. And so if you cover that rock again, it can't get a suntan. So what happens if you go to the beach and you get a sunburn, but then over the next few days, of course, that sunburn goes away? The same thing happens here. If we were to stop production, or like the ice sheet came back over it, that sunburn would eventually go away. In the case of your sunburn, it goes away in a day or two. In the case of a rock, it would take a few million years. But the best way you can think of it is we're measuring the suntan of a rock. And so here are the things we use to sort of sample rock. They're pretty standard tools. So we have a hammer and chisel, a little saw that we use, some safety equipment, our field book, and we actually don't need all that much rock. So right here are just a few chunks of rock. This is probably like maybe 2 pounds of rock in total right there, and that's what we'll take from a site in Greenland and bring it home to our lab. And so where do we sample from? We typically get in a helicopter and we fly around all over Greenland. So here's a nice sample site in Western Greenland. Here's another one. And this site's really unique because my friend here is sampling this bedrock that you can see here. But just like 2 feet behind him is the actual margin of the Greenland ice sheet. So we sampled this site in, I think, July of 2018. And I would bet in like June of 2018, the ice margin was actually over here and was covering this rock. So this rock is this is like the first time this rock has been exposed in thousands of years. And there we are to sample it. And we might come across some wildlife. So this is an Arctic fox. They're not too much bigger than house cats. So in the winter, they get their winter coat and they're a brilliant white. But in the summer, they lose that coat, and you can see it's this brown color that sort of blends in with the landscape. And I'd have to say this is one of the more handsome fox we've seen. Usually they're looking a little more mangy with half of their winter coat still attached, but this one looks pretty good. Another way we might sample rock is we drill cores. So here is this drilling apparatus that we use, and I'm standing on this rock, and I'm gonna drill a core here that's probably several feet long and try to extract that from this site. And you can see the Greenland ice sheet here is in the background. And then here's doing the same thing, but we're goofing around a bit. This is an old friend of mine, also drilling a core. I believe he actually broke the machine not too long after this photo was taken. And then using a handheld little saw, again, you can see in the background, there's the ice sheet that's really close. And again, we're just like taking a few chunks of rock. There's the hammer and chisel. There's another nice sampling site. I know that this particular sampling site, you can see the ice sheet in the background. In the year 2012, this area was still covered by the ice sheet. So this is a really newly exposed landscape. Okay, so we like go all around Greenland and we take these samples and we're able to measure the amount of beryllium in this rock. And so what we can do is we can figure out when in time the ice sheet goes from something big like this to something smaller here. So here we are again on southwestern Greenland. So it would be in this area that I've zoomed in on here. And we want to know, when in time did the ice sheet used to be, when did the ice sheet used to be at this location, and when did it make its way back? So we measure all this beryllium, we're measuring the suntan, and we figured out that about 11,600 years ago is when the ice sheet left the ocean and just began to appear on land. Then 10,400 years ago, the ice sheet margin was a little more inland. 9,300 years ago, 8,200 years ago, and then by about 7,000 years ago, the ice margin had retreated to basically where it is today. So that's sort of how we use this approach to track how the ice sheet is sort of moved through time. The other thing we do is we core a lot of lakes. So if we go onto Greenland, all of these bodies of water you see, most of them are lakes. And so this is how we core lakes. We actually build this sort of like floating raft thing. We paddle out to the center of a lake, and we stick a big tube down there to get a big tube of mud. And by looking at the mud, we can say something about what the ice sheet may have done in the past. And so here's a really nice visual on how we sort of use these lakes. Okay, so what I have circled here is, this is a lake that's in the red circle that's currently receiving water that's coming off of the ice sheet. So here's the ice sheet back here. This is a photograph taken by an airplane back in 1964. And you'll notice this lake, it has a gray color. That's because the water that it's getting from the ice sheet has a lot of mud in it. There's a lot of silt and sand. So that's why this lake is gray. Lakes that aren't gray show up in black here, so these tiny little lakes. So these lakes don't actually get any water from the ice sheet, only this lake does. And here's that same lake in 1985, and you'll notice it's now a dark lake, it's a black lake. So this lake doesn't receive water from the ice sheet anymore. So what does that tell us? Well, we can take a core of mud from these lakes, and we can see those changes in time. So this is a core right here. It's probably about 3 feet long. So you can see up top here and down below, we have this gray sediment. So that's what the sediment looks like when water from the ice sheet is entering the lake. And you'll notice the lake here in the background is one of these lakes that's getting water from the ice sheet. That's why it looks all murky. But at some point in this lake's history, which is represented by this brown sediment here, this lake didn't receive water from the ice sheet, and you get like this very distinct, different type of sediment, right? It's a different color. And so in this lake, here are 2 sediment cores from this lake. So we can tell that in the past, so when you have brown sediment, that the lake probably looked like this. And so thinking about what the ice margin may have done, this is a core from a lake actually right in this area. And we have other ways of taking these cores and figuring out what period of time these cores represent. And so this brown sediment here, we were able to figure out that between 7,000 and 1,400 years ago is when we have this brown sediment. So after 7,000 years ago, the ice sheet actually retreated like farther inland than it is today. So like maybe somewhere in here, or maybe even off the map. And that's when you have all of this brown sediment being deposited in the lake. But then 1,400 years ago, the ice sheet regrew, it came back. And that's why you have all of this gray sediment being deposited in this lake. So that's sort of how we use these these tools in conjunction to say something about what the ice sheet did over tens of thousands of years. And then the last thing that we do is back in the 90s, probably before several of you were born, we drilled an ice core at the center of the Greenland ice sheet. So in the center of the Greenland ice sheet here, there's like 2 miles of ice. And so some scientists got together and they drilled an ice core all the way through the ice. And what happened was, here's that ice core site. They drilled all the way through the ice and into the bedrock that exists under the ice sheet. And so here's actually a picture of that bedrock. And so what we wanted to know is there any beryllium-10 under the center of the ice sheet? So if you remove 2 miles of ice, has that rock ever received sort of a suntan? And so we were able to measure the amount of beryllium, and we found that there's been actually a very long time, or a lot of exposure, 280,000 years of exposure. So that means at some point in the past, probably in many occasions, this entire ice sheet melted away and the rock under the center of it was exposed, and that's how you got the beryllium to form. And so what we're excited about is we have a new project that's starting next summer, where we're going to go to all of these sites where I have a star, and we're going to drill new holes into the ice sheet to collect bedrock that's under the ice sheet to see if there's any beryllium in there we can measure. If there's no beryllium, that means that that site has probably never been exposed to the sky. But if we measure a lot of beryllium, we can say something about how the ice sheet has changed over time. And that's it. Here's the team that I often work with on Greenland. So this is a colleague of mine, Jason Briner at Buffalo. This is another colleague, Leah Lesnick at the University of New Hampshire, Allison Cluett, who's also at Buffalo, Michelle Coppice, who's at British Columbia, Brandon Graham, also at Buffalo, and then your superhero right here, that's me at Beaumont Doherty. And with that.
Great, thank you, Nicolás. So we have quite a few questions here, which I'd love to get to. First, I want to talk a little bit more about your skills and sort of the tools that you've used. If you could talk to us a little about perhaps the team that you've also worked with, what other skills or superpowers other scientists have, and how you all work together kind of to have your superhero group, and how you work with each other, and how you all contribute different talents.
Yeah, so sorry, you cut out there a bit, but I think you were asking about the other scientists I work with and sort of what skills we have.
Yes.
Okay. Yeah, so, we work with a lot of different people, and we all sort of have a different specialty. And so one of my specialties is I do a lot of field work, and I collect these rock samples and we measure, beryllium in these rocks. But we also work with a lot of people who, you'll notice that I showed some of those cores that we took from lakes. So we work with a lot of people who actually go into that mud, and there's different things that are deposited in that mud that these people look at and they measure, and they can say something about how climate has changed through time. So we work a lot with those people. Another superpower, a lot of people can run these really fancy computer models that simulate how the ice sheet may have changed through time. And we work a lot with those people trying to take field observations. So like our beryllium results, or like things we notice in the field, and try to give that to ice sheet modelers and be like, okay, what can you do with this? Does it help your model? Does it help improve your model? So I think those are two, maybe the most obvious other types of people that I work with.
Great, thank you. Okay, great. So we have some great questions here. We've got some questions definitely about animals, what animals you have seen in Greenland or are in Greenland. And, the fox was pretty cool, the photo that you showed. So do you see other animals and birds that we don't see here?
So the other animals we come across are caribou. So there's a lot of caribou running around. The other main animal we see are muskox. So muskox are these large beasts that kind of look like, for lack of a better comparison, like Snuffleupagus from Sesame Street. So those also exist in Southwest Greenland. Those are not native to Greenland. I think at some time in like the 1960s, someone decided that muskox would thrive on Greenland, and in fact they have. And so muskox can really handle that cold climate. And so muskox fur is the densest fur, I believe, on any animal. So if you were to like cut out an inch of its skin or something, it'd be like the most number of hairs per inch of like any animal. In some parts of Greenland, there's polar bears. In Southwest Greenland, where we usually work, polar bears aren't a problem. But if you go to like Eastern Greenland or Northern Greenland, or like across the bay on Baffin Island in the Canadian Arctic, where we also work, polar bears are much more common. So it's something we have to think about.
Apologies, my internet connection is a bit wonky. So I turned off my video. Can you hear me?
Yep, yep.
Okay, great. Okay, so we talked a little bit about the animals. The next question we had was two people asked similar questions. I love that when people start to pick up on similar things. So is there any potential radiation exposure to scientists due to the exposure of beryllium-10 while taking the rock samples? And then someone else asked if you have ever gotten sunburnt when you're on the ice sheet.
Yeah, so the radiation, so there's no danger from the rocks themselves. So that beryllium-10 that's being produced, it's actually held within like individual mineral grains. And there's such a small amount of it, it's not a threat to the scientists or anyone else who like happens to pick up a rock. Where there is a threat, so I mentioned there's like these incoming particles that come from outer space. Those particles, which this is not beryllium-10, these are just particles from outer space. There's more of them in our upper atmosphere, so like in really high elevation, and there's less as you get like towards the ocean. And so there's so many up in the upper atmosphere. It's the reason why pilots and flight attendants have to watch how long they spend in planes. They can't be in planes like over the course of a year for like an indefinite amount of time. They actually have to limit the amount of time they spend in planes because the dosing that you receive is much higher the higher you are in the atmosphere. So that's probably the largest danger, but again, that's mostly to like pilots and flight attendants. And all of those companies, like they keep track of how long pilots or attendants might be up in the sky.
And have you gotten sunburned?
Oh. So, you know, the weather on Southwest Greenland in the summer is actually quite nice. It can be like, you know, mid to high 60s, even the low 70s. But what you really have to worry about is for working on the ice, there's a lot of reflection that comes off of the snow and the ice. And so you might get it, you know, you're exposed to the sun just by being outside, but then you get it a second time and it's bouncing back. So there's been a few times where I've forgotten to put on enough sunscreen. And yes, I've gotten sunburn.
That analogy, I think, works really well. That thinking about the sunburnt, studying sunburn on the rock. So we have a question here about why I think you showed a photo of the ice sediment. Why is the ice sediment gray? I think that was
yeah. So if you think about like a clean glacier, it's usually you think of something that's like white or blue. But when glaciers are always moving. And so when you get to like the margin of a glacier or an ice sheet, like you saw in that photo, this is where you can see where like the bed of a glacier, as it slides across the landscape, it's actually picking up rocks and dirt. And so all of that gets sort of mixed up into the bottom of the glacier. And that's why in some of the pictures you saw, the ice looks really dirty. So what that is, it's a little bit of ice and a lot of like sand, silt, pebbles, and like sometimes even boulders sort of mixed in with the ice. And this happens at the bottoms of glaciers and ice sheets.
All right, great, thank you. a lot more questions about animals, and specifically if you have ever seen polar bears or a baby polar bear, or if any of your coworkers or colleagues that you work with have encountered polar bears.
Yeah. I know there's like the intense urge to sort of see a new animal, but I guess, the dynamics are a little different when this is obviously not a zoo, so you're no longer on top of the food chain here. So we actually don't ever really want to see a polar bear, because then it's probably not good news for us, or we have to really be careful. I've never seen a polar bear while we do work on Greenland. I have seen 2 polar bears while doing work on Baffin Island in the Canadian Arctic. And so, for protection, it's not like we want to use them, but we do carry guns just in case we have an issue. But I've never had to use a gun. I've seen polar bears. I've never had an incident. The 2 times I've seen a polar bear, they looked at me and actually ran the other way, so that was great. And I know of one colleague who's had a pretty serious run-in with a polar bear, but in the end, everyone was okay.
Great. The polar bear probably knew that you had superpowers, so ran away. Yeah. So we have a couple questions here about what it's like to do field work on Greenland. You mentioned the summer is quite nice. It can be in the 60s. What else can you tell us about, what you see in Greenland and the different parts and how those places might vary? And where do you sleep and what do you eat when you're in Greenland?
Yeah, so again, we only do field work in Greenland or mostly Arctic during the summer. And so, our summer, like thinking here about New York, you'd say, like at the end of May, of June, summer's really getting going and it extends definitely into August and most times into September. The weather's a little different up there because we're at such high latitude, we're so far north. So in the spring, for example, like in April, May, it's still really cold up there. So we typically don't start our seasons until early July, if not late July. So that's like peak summer warmth up in Southwest Greenland. And so what you have are really long days, short nights where it basically doesn't get dark. And the weather is, it varies a lot. It can be gorgeous in the mid 60s to even lower 70s. But then the very next day, it could be like the low 40s. So it just really sort of depends sort of day to day. And then 2 days later, you might get snowed on. So it really depends. So a typical field season for us, we get flown out to somewhere basically out in the middle of nowhere by helicopter. We'll set up camp. So everyone sleeps in sort of their own tent. So you're sleeping on the ground in like a pad and sleeping bag. And then we'll probably work at one particular camp spot, usually for like 1 to 2 weeks. And then after, let's say, a week, we call the helicopter with like a satellite phone. The helicopter will come pick us up and like move us to a new camp, and then we'll start the whole thing over. So at the end of one camp, we have to break it down, pack everything up, and we'll move, and then we put camp back up, including like our tents. So what do we eat? So food is a lot of pasta. It's a lot of camp food. And one thing I will say, it's not like we're packing backpacks and we have to carry our own food in. So we're like riding on a helicopter. So it does like allow us some luxury. Usually what we'll do is we actually go shopping months before we go out into the field at like your normal store, like a Wegmans or something. We ship all of that food to Greenland. And so it's waiting for us in boxes. And so obviously this stuff that won't spoil. So there's like a lot of pasta or a little bit of freeze-dried stuff. And then we just bring it with us from camp to camp. Right before we leave for Greenland, we'll get like 30 pounds of cheese to last us, 2 months. And if it's a hard cheese, it won't spoil. But those are sort of the things we eat. If we're lucky, usually working on Baffin Island, we can catch, or one of the local Inuit people will sell us fresh caught Arctic char, which is kind of related to salmon. those are delicious, and it's probably the best camp food you'll ever have. But I'd say all in all, we actually eat pretty well compared to like a normal camping trip.
That's great. Thank you. There's a couple of questions about sort of what is habitability like on Greenland? Are there people who actually live there? And why is it not actually green? I think you get a lot of this question. Yeah, Greenland is not actually green.
Right.
And
so people do live on Greenland. I think the current permanent population is, I believe it's 40,000, maybe 50,000. And so there's a number of towns on Greenland, and they're all in southwest Greenland, or most of the towns, not all, most. So basically right where we're working and where I showed on those maps. And so these are villages that are all out on the coast. And so it's a mixture of the Inuit people who are native to Greenland. And then there tends to be a lot of Danish people who live in these towns as well, because Greenland is technically part of Denmark. And so again, all of these towns are on southwest Greenland. The capital of Greenland is this town called Nuuk. And the population of Nuuk is 12,000. And so that's the largest town on Greenland, with everything else being smaller. The other main town that we work out of, and it's also a really popular tourist destination, is north of Nuuk. It's this town called Ilulissat, and it's a World Heritage Site. That's where the world's fastest glacier is that I mentioned. And I believe the population of Ilulissat is 5,000 or 6,000. Okay, so why is Greenland called Greenland when it's not actually green? Right, so like there's this big ice sheet on Greenland. It's pretty cold year round. Sometimes it's nice in the summer. I mean, the old classic story is, I don't know how much I believe this, but when the Vikings were sailing back and forth from Europe to Iceland to Greenland, they wanted to promote people moving to Greenland. So they named it Greenland, where they needed to get more people to go. And then Iceland, which actually has a much warmer climate, they named it Iceland to try to discourage more people from moving there. Again, I don't know if that's like a myth, but that seems to be the story that's passed around quite a bit.
I like that. In terms of discoveries that you've made while doing this field work and with you and your team, what are some of the coolest things that you have discovered through the research?
Yeah, I think the two biggest things that came to mind was, or that come to mind was, that drilling I mentioned where we're making these measurements in bedrock that currently sits miles below the ice is a pretty, I would say, paradigm shifting result for us. That's just sort of like the new wave of science for us on Greenland. When we got our hands on that rock that they were able to capture after drilling that ice core, our guess was we were going to try to measure all this beryllium, but we weren't going to find anything. So if there's no beryllium, that would mean that ice sheet is basically, some version of that ice sheet has always been there through time. So that site has like always been covered by miles of ice. And then when we found that there's actually quite a lot of beryllium, that sort of shifted our thinking on how responsive this ice sheet might be to climate. And so you saw that number, 280,000 years of exposure. That's not all in one block. That can be split up. So maybe like the ice sheet's gone, you get all this beryllium forming, then the ice sheet reappears, so you stop beryllium, then it disappears again. But so it got us thinking that ice sheet is able to sort of disappear and then regrow on really large scales, repeatedly through the last few million years. And I think that was a shocking discovery for us.
Great, thank you. And here's a question. Did the did the US ever look like Greenland in terms of, I think, probably referring to ice coverage and ice sheets?
Yeah, so that I mentioned that we used to have the Laurentide ice sheet that was covering sort of the northeastern United States. So back 20,000 years ago, a sizable chunk of North America had an ice sheet that basically looked like the Greenland ice sheet, but it was covering much of North America. So what we know now is Canada that was covered entirely by ice. All that's left is like a little ice cap or two up in Canada. And that ice extended all the way down. So it covered Canada. It covered like the state of Maine, Michigan, New Hampshire, Vermont, Connecticut, all of like the northern US, like Wisconsin. And the edge of that ice sheet went down to what is now Long Island. And so Long Island is actually, it represents the southernmost extent of that ice sheet. So, you know, the ice sheet picks up all these boulders and sand, and then it deposits them at the end of an ice sheet. And that's exactly what Long Island is. So if that ice sheet never came down, Long Island simply wouldn't exist. And you can track, there's Long Island-like features all across the northeastern US. But Long Island, I guess for people who are based in New York, is like the best example that we have of the ice sheet being down here. And even though some people don't want to admit it, that includes Queens and Brooklyn too. That's all part of Long Island. It would not be here without that ice sheet.
Great, thank you. So usually, you know, how big is the team that you're working with? And has anyone on the team, again, this is, I think, going back to, you know, just how bright the snow is, and I think your sunburn analogy really stuck. So, you know, how has that snow ever caused sort of your eyes, blindness issues with seeing with the team during field work?
Yeah, so a typical field team for us is at any one camp. It's generally between 4 and 6 people. We've sort of found that's when we're able to get the most amount of work done, but it also, we're limited by basically the helicopter. You know, in a perfect world, we'd actually take more people out there, but you can only fit some. In terms of snow and ice, you know, especially when we're working really close to the ice sheet, it does help to always have sunglasses on because your eyes will notice it. The best example I can give, one time when we were working on the Canadian side, so this was actually in the spring when everything was still covered with ice and snow. We hadn't reached the summer. So we're moving around the landscape by snowmobile. There was one person who was pretty hesitant for some reason to wear sunglasses. And it became apparent after one day that they were starting to have the onset of snow blindness. So that made them put on sunglasses in a hurry. Luckily, we prevented full-on snow blindness, but it is a concern. And for those of you who may not know what that is, snow blindness is basically a sunburn of your eyes. And so it's really painful. You temporarily go blind. So again, you want to make sure you have sunglasses on.
Yeah, definitely. So we have 2 more specific questions about so the types of equipment that you use, and then the kind of analysis that's done after. So so specifically, what types of drill bits are used? Do you do the evaluation on site, or do you keep it stored up and ship it back to Lamont for analysis? And what types of instruments are used in those analyses?
Yeah, so out in the field, really, it's kind of just mechanical brute force to get the rock sample. And so whether we're using like a little handsaw or like that big drill, those are just outfitted with diamond bit drill bits or blades. And so that's just the easiest way to cut rock. And then we can just like chisel it out with a hammer and chisel. And so really in the field, that's all we're doing. But to actually get the beryllium out, we have to take that back to Lamont, and then we have a whole fancy wet laboratory where we do the chemistry, so to speak. And so that takes a pretty long time. So what's usual for us is, okay, in the summer, we'll collect our samples, but we won't have a final beryllium measurement until I don't know, maybe like the following February or March. And so what that entails is all we collect in the field is like a whole rock. So let's say it's like a piece of granite, which is often what we collect. So granite has several minerals in it. We're actually only interested in one particular mineral, and that mineral is quartz. And so when we get that rock back to Lamont, the first thing we do is we have to crush the rock, we have to sieve what's left over, and then we start the process of removing everything else and just holding on to the quartz. So basically, our now crushed rock sample, which is essentially sand at this point, it sits in a lot of very nasty acid baths. And quartz is really resistant. It doesn't like to dissolve. It's a strong mineral, whereas most other minerals sort of are not. And so after weeks to months of acid baths and sometimes hand picking out minerals, all you're left with is quartz. And then once you have quartz, it takes about 2 weeks where we dissolve the quartz. And so now you have quartz and the beryllium that was in that quartz. It's all in solution. It's like, it looks like basically a cup of water. And we'll then spend 2 weeks just removing the beryllium from that solution. And the end result is, after it's all said and done, we dry our sample down and you're left with basically like a pencil point worth of sample that started in a few pounds of rock. And we have to send this little pencil point of what's beryllium. We send it away to an accelerator mass spectrometer. There's only a few of these in the United States. We use Lawrence Livermore National Lab. And so you need these really powerful machines to actually count how much beryllium is in our sample. And so again, you know, it takes many months to do this and a lot of chemistry, and I guess it gets expensive. But in the end, there's only a few places in the US and really only a few places on Earth that can make that final measurement for us. And that's where we send our sample.
Right. So a superhero and his machines and the toys and the gear that you
right.
Okay, we're just about out of time, but I'm going to have two sort of last questions. I think this is a great way to end the session. Brooke and Chelsea have asked, what would you say is your favorite part of Greenland? And then Toby wanted to know, when you were a little kid, what did you think you would be when you grew up?
So my favorite part of Greenland is definitely the Jakobshavn East Spray region, which I was showing on the first slide, the title slide, where it's a World Heritage Site. It's the fastest glacier on Earth. It's extremely scenic. I first went to that site in 2008, and I've been there numerous times since, the last time in 2018. You know, not only is it a gorgeous site, but what we've learned is that for our particular brand of science, mainly how we use this beryllium method, it's just like a perfect system. It's almost like it always works. Like the system was made to work in Jakobshavn. So I'd say that's my favorite site. And what did I want to be? That's a good question. I think at some point in like second grade, I said a chemist. So like not too far off. But I guess the way I got into earth sciences is like your fifth grade like science fair. I don't even know if they still do those anymore. But you know, you're supposed to like design your own project. I didn't really know the details back then, but I concocted some idea where I would go around to like different parts of like the region. I grew up in Western New York, so between like Rochester and Buffalo. And I would collect different types of soil and like different coffee cans. So I think I got like 3 or 4 different types of soil, put it in a coffee can, and I punched holes in the bottom of the coffee can and then just like sat it in water. And I timed how long it would take for water to appear like at the top of the coffee can. And so that was fifth grade science. But at the time, what I didn't realize is I was looking at like the porosity and permeability of rock. And so I guess that's like my first intro into geology, I guess.
That's awesome. Thank you. It does start very young. Yes. Yeah. Thank you so much for your time and for showing us, what it's like to go into the field with you. To our viewers, thank you so much. We had such a great list of questions. If you have any additional questions, I know we didn't get to everything, but if you have anything else, feel free to send me an email. We'll pass it along to Nicolas. I'm sure he'll answer additional questions. Nicolas, any final words from you for our viewers who have asked some great questions?
Yeah, I mean, thanks everyone for coming. I know these are tough times, and you'd probably rather be in school permanently and with your friends. But thanks for joining us online.
Yeah.
And, get outside the best you can.
For sure, for sure. Thank you. That was a good reminder. And for those of you who are going to stay on, we're going to do another session at 4 o'clock. And if you have any additional questions, this was recorded, so we'll get it posted if you'd like to rewatch it. Nicolas, thank you again for your time, and have a good rest of the